time to do some practice involving triple integration, which means that we have some solid three-dimensional shape that we want to integrate over. And the biggest challenge of all is learning to describe the shape and also learning to re-describe it. In other words, I have a description in one scenario where I first say with respect to x and y then z, but maybe I want to do it in some other order. Maybe y then x and z, who knows? There's many possibilities. So we need to learn how to figure out how can we describe these shapes. And the way to get good at it is practice. Oh, who would have thought? Yeah, it takes time and practice to get good at learning to describe these things. And so make sure you're doing as much as you can. If you're following along with the video, make use of the pause button. See a problem that looks interesting? Pause it. Try it yourself first and see how you do. And if you need any help, some clarification, no worries. Just unpause. See, it works both ways. Pause, and it's also an unpause button. Now, the more that you do, the better you'll become, and the more intuitive it will feel. So, keep working, and sooner or later, you're going to become amazing. I believe in you. You can do it. Well, let's begin. Our first problem. We're going to find the integral of the function x squared yz dv over some solid. Well, namely, x goes from 0 to 2, y goes from 0 to 2, and z goes 0 to 1. We can actually draw this solid. It's pretty nice. And if you look, it's like, wow, look. We have x going between two numbers, and y goes between two numbers, and z goes between two numbers. So in terms of the shape, this is a really elegant thing. It's a box where what? X goes 0 to 2, y goes 0 to 2, and z goes 0 to 1. So there we have it, our box. All right. So, okay, here's S. Now, we have to set up our integral. The way we do all integrals is by iterated integration. So, we have to make a decision. Now, when we're doing a box, it's super easy to make decisions because there's almost not a wrong decision. So for us, well, we'll just pick an order. Integral, 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 x squared y z, and so let's do dz, dy, dx. Now, how do we figure it out? Well, we can think about how do we describe our region. The thing is, we have our description. 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 2, 0 less than or equal to z less than or equal to 1. So if we just pair our bounds up, we say, well, look, the outside bounds, the x bounds, right? Because it's dx. So 0, 2. Next layer in, these are y bounds. Y is going from 0 to 2. And the next layer in, those are z bounds. And z goes 0, 1. Now, for these boxes, three-dimensional rectangles, it'll be pretty simple to set up bounds. We're going to do some things which are not three-dimensional rectangles. And in that case, we got to do a little bit more work. Don't worry, more work is coming. I don't want you to think, oh man, we're not going to do work. Oh, you'll do some work. We're gonna definitely turn it up a little bit here. Now, here we're in a good situation. Why do I say we're in a good situation? We can, of course, do iterated integration one level at a time and work through our onion, if you will. But there's two things here which signal that we can kind of speed things up. Namely, you'll see we're in a box. And so, in particular, the bounds are all numbers. So there's no variables showing up in the bounds. Now, that says it's very easy to swap the order of integration. If the bounds are all numbers, then it really is just swapping, the order and life is good. But there's a second thing that's really good. Namely, the way this is written is as a function of x times a function of y times a function of z. In other words, I can think of it, oh, there's an x piece and a y piece and a z piece, and they're multiplying together. So, when we're in this situation, all our bounds, our numbers, were over some kind of three-dimensional box, and our function can be written in the form some function of x times a function of y times a function of z. Then we can do the same thing we did for two-dimensional integrals, which is we can pull them apart. So that says we can think of it in the following way. So we can say, look, we'll integrate the x part. So that's 0 to 2 of, then it's the f of x squared dx. Then we can do the y part. Well, that'll be 0 to 2, and then y dy. And we can do the z part, which is 0 to 1 of z dz. And be careful. You have to have both these things. You have to have nice bounds so that you're really going over a box, and you have to have a function that can separate in this nice way. But now, what we're saying is instead of doing the integrals one at a time, one after another sequentially, we'll say, let's do them all parallel. So we say, okay, this is 1/3 x cubed from 0 to 2. Here, 1/2 y squared, 0 to 2. And here, 1/2 z squared, 0 to 1. Which is, well, we'll have 1/3 times 2 cubed, which is 8/3. Then subtract 0, and so 0. 1/2 times 2 squared is 1/2 times 4, which will be 2. Then we subtract 0. Then we're going to get 1/2 times 1 squared, which is 1/2, subtract 0. And you can see the 2 and 1/2 cancel, so we end up with the final answer of 8/3. And we're done. All right, well, that's not so bad. See, this triple integration, really not so bad. At the end, you have to do 3 integrals. So for each layer, there is an integral involved. Sometimes you have to do them one at a time. You know, it's like an onion where it's like you've got layers. Or sometimes you can do them all simultaneously. It depends on the form of your bounds and the form of your function. Well, that was a nice warm-up. Now that we're getting warm, let's try something else. So, suppose we have the following integral. We're going from -2 to 5, 0 to 3x, y to x plus 2 of 4 dz dy dx. And here, it just says find it. Now, notice, as compared to the previous problem, the bounds are different. You see, the bounds are going to be varying. So there's variables here. So when you have that, you can't pull it apart so easily. So what do? Well, the answer is we do one layer at a time and just work it through. So we say, okay, our first layer is the inside part. So we're integrating with respect to z. Z is our variable. So what do we get when we integrate with that part with respect to z? Well, so we still have our outer 2 layers. So we're going to keep those there. -2 to 5, 0 to 3x, and then the integral with respect to z for z. Evaluate, and the bounds here are z bounds, so it's good to remind ourselves. Z equals y to z equals x plus 2. And then dy dx. So we integrate, then we evaluate. So that would be what? Going from -2 to +5, 0 up to 3x of 4 times x plus 2. So you can write that as 4x plus 8. So that's when we plug in the top. Subtract 4 times y. All right, there we go. And we're going to integrate dy dx. Okay, so we integrate the inner layer and evaluate. All right, well now we do it again. Say, okay, go to our next layer. There's our next layer, and we're going to integrate that. And now we're integrating with respect to y. So what will that be? Integral -2 to 5 of, well, we integrate with respect to y. 4x and 8 are going to act like constants because they don't involve a y term. So 4xy plus 8y, integral of minus 4y with respect to y, minus 2y squared. And then we're going to evaluate, and there are our y bounds. Y equals 0, our favorite bound, 0. And then y equals 3x. All right, good. So now we need to evaluate. The nice thing is when you plug in 0, 0, 0, 0. Good. What happens when we plug in the top bound, 3x? Well, we're going to get 4x times 3x. So that would be 12x squared. And we're going to get 8 times 3x. So that's 24x. And we're going to get minus 2 times 3x squared. Okay, if we square that, we'll get 9x squared times 2. So that'll make it minus 18x squared. All right. Well, before we integrate, we say, look, we can combine those terms. So we have 24x, then minus 6x squared, and dx. So now we're like, wow, we know how to do these. We've known how to do these for a long time now. So integral of 24x, 12x squared. Integral of minus 6x squared. Well, that'll be minus 2x cubed, right? Because here, integral of x squared is a half x squared. 24 times half is 12. Integral of x squared is a third x cubed. 6 times a third is 2. And you plug in from -2 to 5. Excuse me. Well, all right. So we get our answer 12 times 25 minus 2 times 5 cubed. Okay, that's 125. Subtract 12 times 4, right? Because -2 squared is 4. Then minus 2 times minus 8. Well, if we wanted to, we could simplify a little bit. For example, 12 times 25 is going to be 300. 2 times 125 is 250. So there's that. Then here we have 12 times 4 is 48. This will become plus. Here, 2 times 8, 16. The reason it's plus is 2 minuses. So 300 minus 250 is 50. Then we're going to subtract 48 and also subtract 16. Well, if you take 50, subtract 48, that's 2. That's easy. Now you subtract 16 more, and we end up with -14. And there we go. Now you might be thinking, this is kind of a weird answer. And you might say, well, why is it a weird answer? We got a negative value. Now, it's not bad to get a negative value out, and it happens. But why it feels weird is because what we're integrating is a positive thing. So it's like, wait, we're integrating a positive thing over some region, and why do we end up with a negative answer? Well, okay, so here's why that happened and why it's okay, at least for now. The reason why it happened is if you look at your shape, in some sense, if you were to plot what's happening here, it's kind of weird because you have things going in the wrong order when you have certain bounds. And so because you have things going in sort of the wrong way. You have some parts that are contributing negative, some parts are positive. To be more clear about what do I mean by this is just think about what's happening with the outer two layers. So what does that tell us? The outer two layers say that x goes from -2 to 5. Okay, so here's -2. Let's say over here is 5. And then we're going for y from 0, which is the axis, up to 3x. And you can see, oh, here it's sort of the right orientation, positive. Down here, whoa, negative. And so because you have that sort of weird thing happening, where it's like, oh, the bounds are kind of off. Now, that's if we had gone to set up the bounds ourselves. We would have said, hey, something's suspicious here. But since it was handed to us and they just said, hey, do this computation, we said, okay, we'll just do the computation as given, and we'll see what comes out. There are reasons to say, look, don't worry about the order that the bounds are in. And of course, there's other reasons when you say you do want to worry about it. But if a problem is just given to you, just go with it and say, all right, whatever it is, positive or negative, that's the result. As long as it's just an integral. Of course, if they say, do this to compute a measurement of something, and you know, wait, the measurement has to be positive, then we should be nervous. But for now, we're okay. We're okay. All right. Well, interesting. Well, let's try another one. Another good problem. It shouldn't be too hard to find more good problems. Find the integral 0 to 1, 0 to 1, 0 to 1. Ooh, nice. We can even see, look, z goes from 0 to 1, y goes 0 to 1, x goes from 0 to 1. It's a box. All right. Anyways, so we're going to find the integral over this box, this 1 by 1 by 1 box. And our function is y squared x, then e to the xyz, and then dx, dy, dz. Now, one of our first thoughts might be like, wow, this seems pretty nice. Do we really have to do much work? Well, can we do the pull this integral apart into pieces thing like we did a little while back on an earlier problem? And the answer is no, we can't. See, this thing right here, this function, does not have the form some function of x times some function of y times some function of z. So it doesn't have the ability to be pulled apart. And really, the problem is up here in this exponent. And now we look at it and say, okay, so we'll just iterate one at a time, right? That doesn't seem so bad. Except we look at the first one and say, ooh, if we do our first integral, we're integrating with respect to x. And that would require us to say there's an x there and an x there. 2 x's. That's a lot more x's than I want to deal with. So, what can we do? Well, what we can do is either say, let's just go for it, and we'll do some integration by parts, or there's another alternative, which is say, hey, we have to do 3 integrals. What we can do is say, let's pick an integral that we want to do first and make a decision. So suppose I wasn't told it was in this order. I just said, look, I'm integrating over the box. What order would I prefer? Well, if we integrate with respect to x, there's 2 x's, so that's the product rule. With respect to y, it looks even worse. But notice, with respect to z. With respect to z, it's great, because there's only one z. All right, so we say, ooh, we should change the order. Okay, so let's change our order. Now, one thing we might try to think of is, what's the right order? Now, what do we see? Well, it doesn't really matter the bounds. It's always 0, 1, 0, 1, 0, 1. Function is still the same. And we see, well, let's first integrate with respect to z. And then we have to say, what do you think, x or y? Well, we can always change our mind later. It looks like x is, the y looks most complicated in some sense because of y squared, and the x looks slightly simpler. So there's sort of this idea, let's put off anything complicated as much as we can. It's kind of reasonable, right? It's like, well, let's try to make progress when things are simple, using simple things, and then once we've exhausted that, then we'll try to do more complicated things. So I would say, based on what we see here, let's try dz, dx, dy. Okay, well, sure, we can do that. So does it help? Well, let's see what happens. So our first layer. So here, we're integrating with respect to z. So x and y are going to be treated like constants. So when we integrate, well, we'll still have the outside layers, 0, 1, 0, 1. And now, well, this y squared x will still be there, okay. Then we're going to have e to the xyz, but we have to divide by this extra constant in front of the z. So we're going to divide by x times y, and then evaluate our bounds, our z bounds, z equals 0 up to z equals 1. Okay, so that's our first layer. Let's clean up and see what we have. Very conveniently, we have some terms in front to cancel. Pew! And then we have another pew! Oh, beautiful. So it's just going to be y times this expression. Okay, so integral 0 to 1, integral 0 to 1. Then we have y, e to the xy. But don't forget, you have to plug in 0, because e to the 0 is not 0. E to the 0 is 1. So we're going to have minus y, because it's y times 1. Okay. Now we're ready to do our next layer. So our next layer is going to be here, where we go with respect to x. And we're pretty happy with respect to x because there's only one x involved. See, if it had been with respect to y, I'd be like, still have to do parts. But here, single x, we can make progress. So we keep going. So what do we have? Integral 0, 1. Here, well, we would have that y, e to the xy. Then, because right, this is a constant when you think about with respect to x. And, all right, integral of e to the x times something is e to the x times that something. Divide by that something, right? You have to account for that constant factor. When I put constant in quotes, because of course, with regards to integrating with respect to x, we do treat y as a constant. And then here, integral of y will be x times y. And then we're going to evaluate that. These are x bound, so it's good to keep track of what they are. So we'll write this as x equals 0 to x equals 1. And there we go. Now we can do a little bit of cleanup. Pow, pow. That's nice. And what do we have? Well, let's plug in 1. So we have integral 0 to 1 of e to the 1 times y, which is e to the y, then minus 1 times y, minus y. When you plug in 0, we'll have e to the 0, okay, which is 1. That's being subtracted, right, because you subtract the lower bound, and then this will be 0. So it's the integral 0 to 1 of e to the y minus 1, and we're doing it dy. All right, well, we're almost there. Okay, here we go. Integral of this, that's not so bad. Everything's happy. Wow. See, we started this thinking, boy, integration by parts. But no integration by parts were needed. So integrate each piece and evaluate 0 to 1. So what do we get? Well, plug in 1. We're going to get e to the 1, which is e, minus 1/2, minus 1. remember, he also has to subtract, plug in 0. And e to the 0 is 1. Okay, so 1, then 0, 0. So, well, it's e minus a half minus 1 minus 1. Well, that's really minus 2.5, or minus 5 halves. So our answer is e minus 5 halves. And we're done. Now, on a side note, e minus 5 halves is a fairly small number, but that's okay. We're not really going over a very large region, and the values that we integrate look like they should be fairly small because we have these factors of x and y in front. So there we go. E minus 5 halves. Wow. Good. Nice. Good, fun problem. And this shows you, hey, sometimes order matters. Because you can imagine if we had started by doing integration by parts, it would have been disaster. We would have gone to points where it's like, we can't even integrate this anymore because it doesn't work anymore. So you should always think about a problem and say, have they really given this in the nicest format? If not, is there a nicer way to write this problem? Because remember, we really want to be nice to ourselves. We love ourselves, and we want to make sure that we put ourselves in the best situation for us to succeed. Okay, good. On to our next problem. Here we go. Ooh, something different. Change the order of integration. So we have integral 0 to 4, integral 0 to 2 minus a half z, integral 0, 1 minus a half y minus a fourth z, f of x, y, z, dx, dy, dz, 2 dz, dy, dx. All right. So we actually don't have to do any integration. This is all about setup. Do we understand the setup? Well, so let's begin. Now, the way we begin is we're trying to say, look, we want to change the order of integration. So the first thing we have to do is say, let's understand our region. So we're going to figure that out from our bounds. So how do we do that? Well, remember, these are actually attached to variables. So, for instance, the 0 to 4 goes with the z. So we know that 0 less than or equal to z less than or equal to 4. Now, we can draw that. So if we think of this as z, we're saying we're going from 0 up to 4. Okay, well that's pretty straightforward. No big surprises there, but we keep going, right? Yeah. Now let's go to our next layer, which is y. What does that say? Well, we're told that, see, these are y bounds, so y equals 0, or really 0 less than or equal to y, up to 2 minus 1/2 z. So what we can now do is if we think of the first integral on the outside as between two numbers, when we push in, we can say now we have two integrals. It's a two-dimensional thing. In this case, it'd be in the yz plane. So we could say, all right, we're going to take our z, so here's z, and then we're going to do our y. Now, we know that z is going from 0 up to 4. Okay, that's what we inherit from the previous problem, or rather I should say the previous bound. And now, well, where does y go from? Well, we're going from where to where? We're going from y equals 0. Now y equals 0 is this. It's the z-axis to the curve y equals 2 minus 1/2 z. Now, what does that look like? Well, another way we could write this is we could solve for z. So we could say, look, 1/2 z is equal to 2 minus y, or z equals 4 minus 2y. So we start here at 4 is the intercept, and then we have a slope that goes down by 2. So So it goes down pretty quickly, and it hits here at 2. So we're going between this curve and that curve. So we're going this way. So the outer two integrals tell us we have a triangle in the YZ plane. Okay, we still have one more layer to go. So our last layer is here. It's an x. So we are told we start x equals 0, and then we're going to go to 1 minus a half y minus a fourth z. Okay, well, let's unravel this. We have our axes still. We have our z-axis, right? We have our y-axis. Sure, no problem. And now we have our x-axis that we're going to acquire new information about. We also know that we have this triangle here. We'll just sort of quickly sketch it in. There's here at 2. I'll just lightly dot it, just for reference here. And now we have to say, well, what's happening with our x? Well, we're going to go from one plane to another plane. Now, of course, in general, it's one surface to another surface, but what we see here is that we're going to have x equals 0. Well, x equals 0, that's this YZ plane. And we have to be on top of this triangle, but really we can say restricted to this triangle. Just like here, we're restricted to go from 0 to 4. Well, we're restricted to go over the region that we had from the previous step. So that's one surface, and then we're going to move to another surface. So what's our other surface? Well, it'd be the surface x equals 1 minus a half y minus a fourth z. I almost wrote y twice. I don't know why. If we rearrange this, we could say, oh, this is x plus a half y plus 1/4 z equals 1. Okay, and now in that form, we're like, yes, that's very plain. It's a very plane-like thing. Cool. Now, what can we say about this plane? Well, we can say a couple of things. Where does it hit the three axes? So suppose I want to know where I hit the z-axis. Well, on the z-axis, x and y are 0, so it would be at where 1/4 z equals 1. Oh, well, that's at z equals 4. That's good. How about where do I hit the y? Well, x and z are 0, so half y has to equal 1. Oh, that's at 2. Where do we hit x? Well, the y and z are now both 0, so we hit it at x equals 1. So in terms of the plane, we can now do connected dots because we have those 3 points. 3 points determine a plane. And what's going to happen is we're going to go from this back face here, which is the x equals 0, and then we're going to keep moving forward to the front. So what we end up forming is we're going to move from the back to the front. So we get this tetrahedron. So there we go. There's our shape. We say, aha, tetrahedron. So we've come to the conclusion that we now know how our region looks like. That's step 1, more or less, is what region are we integrating over? Now, what's the next thing? Well, the next thing is we say, now that we know our region that we're integrating over, and we can think about our surfaces that bound. Now, a tetrahedron has 4 faces, and so there's 4 surfaces which are involved. We can mark them all pretty simply. So, for instance, this back face here is the YZ plane, x equals 0. This bottom face, that's the XY plane, z equals 0. This other back face, well, that's the xz plane, y equals 0. And then there's this part, this plane there, which is the plane that we have right there. So x plus a half y plus a fourth z equals 1. All right, so now we've marked everything. We're ready to start working on our bounds. So, great. Let's set things up. So we're going to have an integral, integral, integral. And if you're wondering why I put more space between the first and second versus the second and third, the answer is between the first and second, it's always between two numbers, which tends to be small things to write. From the second to the third, my bounds are curves. That can be a little bit longer to write. And here, it's going to be the bounds are surfaces, which could be even longer. So you want to give yourself enough space. Well, that or just be ready to rewrite. So dz, dy, dx, and now we're ready to start. So there are different philosophies about how to find the bounds. I'm going to talk about the way I like to find the bounds because it's what works for me, and I think it's intuitive. And so what we should do is work one layer at a time and work from the outside in. So I want to work from the outside going in, which means I want to figure the x bounds first. Well, how to do that? Well, let's think about the last things we have to figure out. It's the z. So what we can do is we can say, look, let's take this z-axis here, and we're going to imagine that we pivot so that we're going to look straight down the z-axis. So we're taking our z-axis and pivoting it so that we look, lo and behold, it looks like a single point. Why do we want to do that? Well, because it's the last thing we want to determine, it helps for us to sort of not have to think about it, to not be distracted by it. So by looking down the z-axis, what we're saying is, what's the solid in terms of the xy plane? What does it cover? And so that helps us figure out what the outer bounds are. So looking down the z-axis, we see, aha, in the xy plane, what we'll see is the following. We're going to see there's that x equals 1 and y equals 2, and we're going to see a nice triangle. Say, all right, good. So in particular, looking down the z-axis, we say, and our solid needs to have our bounds for x and y be determined by this shape. Wonderful. Okay, well, let's think about it. We're talking about x, so where does x go from? In other words, the smallest value of x that we hit to the largest value of x that we hit, and we can see from here it's 0 to 1. All right, now once we have our x picked, we say, okay, with our x picked, what will happen is our y will go from some curve to some other curve. So we have to say, where are these curves? So one curve is pretty simple to spot. It's this curve, which is y equals 0. So 0. And now there's this other curve here. Well, what is that other curve? We can think of it as a line. So, and this is a y bound, right? So we want to think of this as y equals something. The intercept here is at 2. The slope, we go down 2 over 1. So the slope is minus 2. So 2 minus 2x. That's this line that we need to go up to. So 2 minus 2x. All right, we've done the outer, we've done the middle, one more to go. Now let's go back to our 3D picture and think about what we need to do. So we have our x, our y, and our z, and okay, we have our shape. It's our tetrahedron, so we'll mark our points here. And now what we're thinking of is where do we move in terms of z? So when we're thinking about where to move in terms of z, that says, hey, we're moving parallel to the z-axis. So we're going straight up and down. So in terms of where we move, we say, okay, what's the bottom surface and what's the top surface? So we say, okay, there's the bottom surface and there's this top surface. So the bottom surface is this surface, z equals 0. All right, well, that's great. That says that this here is 0. Where's the top surface? Well, the top surface is this face of the tetrahedron. All right, well, what is that? That's the plane. But not just any plane, this particular plane. So we have to say, well, let's dig into it. We don't write down this plane because why? We need to have it, it's a z-bound, so we need to have a z equals. So our top surface, x plus a half y plus a fourth z equals 1. And now solve for z. So 1/4 times y is equal to 1/4 times z. Silly mistake. 1/4 times z, 1 minus x minus a half y. And now multiply by 4, and what do we see? Z equals 4 minus 4x and minus 2y. So that is this plane where we solved for z in terms of x and y. And we're done because we've got the bounds. So what we've done is we've said, hey, you know, the original shape, this tetrahedron, originally it was defined as a series of 3 inequalities. So the 3 inequalities that we originally had, 0 less than or equal to z less than or equal to 4, 0 less than or equal to y less than or equal to 2 minus a half z, and 0 less than or equal to x less than or equal to 1 minus a half y minus a fourth z. And what the changing the order of integration has done says, oh, by the way, we could also have done it as the following. So equivalently, this same region is described by saying that x goes from 0 to 1, that y goes from 0 to 2 minus 2x, that's the next layer, and that z goes from 0 up to 4 minus 4x minus 2y. So these 3 inequalities will describe the same 3-dimensional shape as those 3 inequalities. When we talk about changing the order of integration, that's essentially what we've accomplished, is saying let's trade one system of inequalities, a description, for another system so that we can get our bounds set up. You can imagine, kind of subtle, not so obvious all the time, because it's kind of subtle and not so obvious all the time, which is why practice is important. All right, good. Well, if practice is important, we should keep practicing. So here we go. Let's do another one. Let D be the solid where x, y, z is greater than or equal to 0, and y is less than or equal to 1, and x plus z is less than or equal to 1, and z is less than or equal to 1 minus y squared. All right, and they gave us a picture here. And, all right, so find the integral of 30 dv. Interesting. Then there's this sort of cryptic hint, dx, dz, dy. We'll come back to that hint and talk about it. Now, the good thing is we don't have to be artists. They were nice, and they actually said, look, we will draw these pictures for you. Thank you. Okay, so let's talk about our various bounding surfaces. Some of them are pretty easy to spot. We see there's actually going to be, let's see how many, it looks like 5. So there's this surface down here which is the xy plane. So that corresponds to z equals 0. There's another surface over here, which is the xz plane. Okay, that's y equals 0. And then there's one other, which is this flat surface here. Okay, and that is in the yz plane, which is x equals 0. So those are 3 of our faces. There's more to do, though, right? So that's essentially the x, y, z greater than or equal to 0. And then we have some other things. It says y is less than or equal to 1. Well, we'll get to that in a second. It's not so clear where that is. We're also told that x plus z is less than or equal to 1. Now, notice it only has 2 of our variables, right? X and z. So if we think about it in the xz plane, it would say, okay, it's a line in the xz plane. And it's a line which passes through x equals 1 and z equals 1. So this is x plus z equals 1 in the xz plane. In 3 dimensions, since there's no y, you would just translate that back and forth. So what's going to end up happening is that this face over here, this is going to be the face x plus z equals 1. Okay, that's right there. Now, z less than or equal to 1 minus y squared. You'll notice there's no x. So you can say, okay, well, let's think about it as just sitting somewhere here in the, say, the yz plane. And if we did, well, it's a parabola, and z equals 1 minus y squared would start over here at 1, and be going up. So this is the part where we have z equals 1 minus y squared. But now, again, since there's no x, we can imagine it being copied back and forth. So what happens is that curved face here, this is the face z equals 1 minus y quantity squared. Now, the y less than or equal to 1 really doesn't show up as a face. It just says we aren't going to go anything past that. The reason that that's thrown in is, well, you can imagine that after z equals 1 minus y squared, it turns back up again, and we want to make sure we're not including anything over there in the solid. Great, good. So now we have an even better understanding of our solid than we had before. We know each one of the bounding surfaces. What are they? So the next thing for us to do is to work on setting up our integral. Now, they didn't say that we have to go in any particular order, but they did give us a hint, right? Because they just said, well, find this integral. Oh, by the way, dx, dz, dy. Well, what is that dx, dz, dy? That's a possible order of integration we could do. So I think we should probably follow what they suggest. So we are going to work on finding the integral of 30 dx, dz, dy. Okay, so if this is our order of integration, perfectly reasonable order, nothing wrong with it, let's think about how to go about setting up our bounds. Now, work from the outside in, which means that the last bounds to set up are the x bounds. So we're going to imagine that we're starting here, and we're going to tilt so that when we look down the x-axis, we don't see anything. So we're just picking it up, and we're just going to be like twist and boom. So that when we look straight down the x-axis, so the x-axis becomes like the origin. So here's the picture. So look down the x-axis, and the reason we're picking the x-axis is the inner layer is x. What will we see? Well, we're going to see the y-z plane. In other words, the other variables. And not only will we see the y-z plane, we can actually see what will happen is we're going to see this parabola piece that was showing up, where here's 1, and here's this curve z equals 1 minus y squared. Okay, so good. We now have our region. And our next thing to do is to start thinking about our bounds. Well, let's start with our outer layer. Y. Where does y go between? Well, smallest value of y to largest value of y, we're going 0 up to 1. So 0 to 1. Great. So now suppose we know our value for y. Where does z go between? Well, we're going to go from curve to curve. So what are the curves? The bottom curve here is the curve z equals 0. So we're going to go from 0. The top curve is the parabola, 1 minus y squared. All right, good. And now we're ready to push in one more layer and do the x. Now, go back to the three-dimensional picture. Because we want to ask, where does x go from where to where, it really says, hey, we're running parallel to the x direction. So we're thinking, all right, as we move back and forth, what surfaces are we hitting? What surface do we hit, at each end? So our back surface is that surface, and it's the surface x equals 0. Okay, so that says our lower bound is 0, which is good because we want to x equal something. There's x equals 0. And then what will happen is we're going to move forward. All right, so if I start here and I move forward, I'm going to stop when I hit this other surface. So this surface, which is x plus c equals 1, will be the other bound. Now, we have to take that surface, x plus c equals 1, and we have to rewrite it in the right form, where the right form is x equals, because it's an x bound, so it should be x equals something. All right, well, if x plus z equals 1, then x is 1 minus z, right? X equals 1 minus z. Okay, great. Now we're set up. But it said find it, right? It didn't just say set up the integral. We're going to find it. So here we go. Okay, this should be fun. All right, what can we do? Well, it's one layer at a time. So we'll start with the innermost layer. So we get that this will be equal to integral 0 to 1, integral 0, 1 minus y squared of 30x, evaluated from x equals 0 to x equals 1 minus z, and dz dy. Okay, well, what will that be? 0 to 1, 0 to 1 minus y squared, and then here, multiply through, we're going to get 30, and all right, 30 times 1 minus z, all right, we can write it as 30 times, well, we'll write it as 30 minus 30z. Why not? Why not? Okay, great. Well, keep going, right? So, what's next? So the next one, we go to our next layer. What's our next layer? What will it be? Okay, so we're going to integrate here with respect to z. So this will be integral 0 to 1, integral, well, what? Well, 30z minus, and here, well, it'll be z squared over 2 times 30 makes 15 z squared. And we're going to evaluate from z equals 0 to z equals 1 minus y squared dy. All right, well, That's integral 0 to 1 of 30 times 1 minus y squared minus 15, 1 minus y squared squared. That's 1 minus y to the 4th. All right, wow. Okay, now the good news is when you plug in 0, you get 0. Great, wonderful. Except you're like, are we really going to have to take that and expand 1 minus y to the 4th? No, we don't have to do that. But what can we do? Well, what we can do is do a nice substitution. Why not? We're allowed to do that. So let's make u to be 1 minus y. Okay, then we get that du is minus dy. So that's not so bad. Or to put it another way, minus du is plus dy. So, what will we have? Well, our bounds will become, instead of 0 to 1, will be from 1 to 0, right? Because 1 minus 0 is 1, and 1 minus 1 is 0. And then there's going to be a minus here, and then we're going to get 30u squared minus 15u to the 4th du. Well, if you really object and say, I really like the bounds in the right order because I just really prefer it, no problem, just switch the bounds. If you switch the bounds, what should happen? Well, you have to get rid of a negative. Well, that's actually good. That's actually, we like that. 0 to 1, 30u squared minus 15u to the 4th. All right, well, now we're ready. Integral of 30u squared, well, you integrate, you'll get 30 times 1/3 u cubed. So that's 10u cubed. Here, integrate, that'll be 15 times 1/5 u to the 5th. So that'll be minus 3u to the 5th. And we're going to evaluate from 0 to 1. Well, plug in 1, you'll get 10 minus 3, which is 7. Plug in 0, you'll get 0 minus 0, which is 0. And therefore, our final answer is 7. And we're done. Wow, that's amazing. That's actually really cool. So you look at this problem, you probably wouldn't have guessed 7 was the answer, but it worked out really, really nicely. Now, on a side note, this is a problem from an old exam. And this particular problem was number 7 on that exam. Wow, coincidence? No, we just had fun, right? We come up with a problem where it matches the number. Never say that. Mathematicians don't have fun. We have a lot of fun. All right, well, let's try another problem. Of course. So, let S be the solid in the first octant. Sometimes people say the positive orthant, but basically we just mean x, y, z are all greater than or equal to 0. And we have some bounding, looks like surfaces, right? Because we're in 3 dimensions. In 3 dimensions, we don't have bounding curves, we have bounding surfaces. So we have z equals 0, y equals 0, y equals x, and z equals 2 minus a half x squared. Well, good. And then it says, write this integral as an iterated integral. All right. Now, let's think about the picture, because it's important to understand the various pieces, how everything fits together, and where the bounding surfaces are. So let's just start by pointing some things out. We'll start with the easy stuff. Okay, we can talk about z equals 0. Well, that's really simple. Z equals 0 is the floor. It's the xy plane. Okay, so there we have the xy plane. All right, so that's one of our bounding surfaces. Okay, what's another one? Well, y equals 0. okay, what does y equals 0 look like? Now, if you look at y equals 0, it was the xz plane. Now, where does the xz plane fit in? The xz plane, if we think about it, okay, so this is our x, y, and z. So the xz plane is this part right here. All right, so there's another one of our bounding surfaces. Okay, well, so far, so good. Okay, what's next? There's the y equals x. Now, let's think about this one. First off, it's a plane. You could rewrite it as, x minus y plus 0z equals 0, so it's a plane. Even if we didn't see it was a plane, one thing we could say is, oh, this is really familiar. The line y equals x, yeah, we know what that looks like. Okay, we know definitely what it looks like in the xy plane. It's one of the first functions that we ever learn about. So we say, okay, well, what does it look like in three-dimensional space? Well, what we can do is we say, okay, we start here in the xy plane. It comes in as a line of some sort at 45 degrees. All right, and then we can just imagine copying that line straight up and down. So it's a plane. So one way you can think of it, notice that we had that plane y equals 0. You could imagine that we take the z-axis and we pivot it 45 degrees. So you take this and you pivot it 45 degrees and you'll get that plane coming out. All right, so there we go. Okay, so there's the plane y equals x. Now, what's the last piece? Well, the last piece is going to be z equals 2 minus 1/2 x squared. Okay, well, what will that look like? Well, think about the xz plane, because there's no y, so we should start with just x and z, and we say, hey, if it's in the xz plane, we can visualize what that would be. That would be a parabola. It would be a parabola where it's going down because of the minus attached to the x squared, and it's been shifted up. So we can think of it as coming up here to 2 and opening down. And so that's the parabola, and of course it's just going to translate over. Since there's no y, it just goes across. So there's the picture. It's coming down. Now we start thinking about what would happen if we put all of these things together. And in particular, where do they start to intersect? Because that's a key, is if you can figure out where things start to intersect, then you can start to say, here's how they all come together into one shape. And hopefully we have enough space here. Okay, so, probably not, but shh, don't tell anybody. Well, some things are easy to spot as intersections. So for example, z equals 0, y equals 0. Okay, that's the intersection is down there. Y equals 0, y equals x. Okay, there's an intersection that fits in there. And where else do we see? Oh, here. Where this comes down, it does hit the xy plane. So that'll be something that fits right around there. Okay, what else? Well, this will also hit the y equals 0 plane. Okay, so there's an intersection. And then there's one more thing that looks like it'll be interesting. Namely, if I look at these last two. So, if we look at y equals x versus z equals 2 minus half x squared, it's going to come down, right? So we have this sort of other piece coming down in some way. All right, and there we go. And I should have pointed out that there's also this intersection here, which corresponds to that point. So that's our shape, actually. This is it. We have all of our pieces coming together, and now we can start marking where certain things happen. So, for instance, here, this would be at 2. Z equals 2. How about here, this point? Well, where would that be? Well, that would correspond to where z equals 0. So we need 2 minus a half times x squared to equal 0. Whoops, I wrote z here. I meant to write 2. So when does 2 minus a half x squared equal 0? Well, that's the same as x squared equals 4, or x equals 2. Oh, okay. So this point over here is at 2. All right, so this point here is at 2, 2. Okay, good. And this point, 2, 2, 0, it's a three-dimensional point. Gotta make sure we get all the coordinates in. And down there is at the origin. So, we are almost there. We're almost there. And we already have the formulas for the surfaces marked. So that'll be a handy reference. And in here, let's do one other thing with this surface. And namely, right now it says z as a function of x. We could have written it as a half x squared equals 2 minus z, or x squared equals 4 minus 2z, which says that x is square root of 4 minus 2z. It's the positive square root because we want to assume x is positive. So we have all 4 of our bounding surfaces described in nice and all possible ways. So in other words, look, I can solve here y equals x, or x equals y. Here I have z as a function of x, or x as a function of z. So what's the last thing to do before we set up our bounds? For me, the last thing I would want to do before I start setting up the bounds is to say, what happens as I look down the various axes? And once that's understood, the rest probably won't be so bad. So, there's some space. Well, okay, down the x, well, let's start with the z-axis. That's usually the easiest. So if I look down the z-axis, I'm looking straight down. I see the xy plane. What do we see? What's there? We see a triangle. That triangle down below. Okay, well, that's fantastic. And we can even see, well, where does that triangle sit? It's going to be here. So it's going to run a little bit along the x-axis, and then there's line y equals x, and it goes to this point 2, 2. So that's the region if we look down the z-axis. That's what we see. Now, what if we look down a different axis? Well, suppose we look down the y-axis. Okay, now the y-axis, that's this axis here. When we look down, what do we see? Well, what we'll see is this shape right there. All right, so there we go. So that is in the xz plane, and it's this, we come here at 2 and come down here, and here's 2 as well, and this is our curve z equals 2 minus 1/2 x squared, or x equals the square root of 4 minus 2z. Okay, so that's what we'll see, and then the one more is, of course, what would happen if we look down the x-axis? Okay, this one's the interesting one. This one's interesting. Like, look, I know they're all interesting, and I know, but believe me, what do you see? What is it that you see? So we're looking down this axis. What is the part that we see? The answer is we see this face here, this part of this sort of sheet. That's what we're going to see. Now, parts of it are easy to spot. We say, okay, well, we're going to have something that comes down here. It's going to hit here at 2. It's going to hit up here at 2 there. Then there's some curve that does that. What curve does that? Because remember, this here is the YZ plane. So what's the right curve? Now, how do we find it? Here's the really cool thing. It turns out, we say, well, wait a second. This particular curve, this curve that we're trying to identify, so let me mark it. This curve right here. Well, it's the intersection of y equals x and z equals 2 minus a half x squared. So I say, oh, wait, I can replace x by y. So this is z equals 2 minus 1/2 y squared. And of course, I can also solve for y, so that's the square root 4 minus 2z. Okay, so now we have our beautiful pieces all set to go. And of course, the one thing that we really don't have now is a lot of space to write down our answer. We'll get some more space here in just a second. So let's redraw for reference our solid. So now that we have a better understanding of it, so we're going to have a couple of curves here. So we have one, boom, boom, and we have this line, and there we go. Okay, and we'll mark the planes. I'm going to do that here really quickly. Z equals 0. Y equals 0. This is x equals y, or y equals x. And then, of course, this front plane, this is our z equals 2 minus 1/2 x squared, or x equals the square root of 4 minus 2z. All right, so here we go. Let's ask the question. It says start it as an iterated integral, which means we have a choice. We actually have how many choices? 6. We can have 6 different possibilities. And it didn't tell us which one to do. So let's do all of them. Just so we can be like, wow, we definitely can get this done. All right, so we're going to cover up some space here. And let's see, I think we can make this fit just about. Okay, that's close enough, close enough. So we'll begin. We're going to do integral, 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 our function, f of x, y, z, and then we'll do dz, dy, dx, and then integral, 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 f of x, y, z, dz, dx, dy, integral, 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 f of x, y, z, and now we'll do dy, dz, dx, integral, 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 f of x, y, z, dy, dx, dz, integral, 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 f of x, y, z, and dx, dz, dy, and integral, 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 f of x, y, z, dx, dy, dz. All right, well, 6 to do, and let's begin. So, suppose we start with this first one. So we have dz, dy, dx. So here we say, look, z is the last thing. Let's look down the z-axis. Great. So I'm looking down the z-axis, and we start by saying, well, where does x go from, right? So here we say, x goes 0 to 2. All right, there's our outer layer, 0 to 2. Now, where does y go from? Well, so I'm going to go from the bottom, which is y equals 0, up to this curve, which is y equals x. So, remember, we want it as y equals something, so it's going to be y equals x. Now, what is dz? Well, for dz, we say, okay, think about the picture. That says, for dz, I'm moving in the z direction. So I'm going to move up and down. So we say, okay, we're going to start down here and move up there. So we're going to go between two surfaces. And the bottom surface is this z equals 0. Okay, so we're going to go from 0 up to this curved surface here. So that is z equals 2 minus 1/2 x squared. All right, one down. Now let's go to the next one. Okay, well, let's look at y. So we think about, okay, where does y go from? Because again, look down the z-axis to start. Y goes from, lowest value is 0 up to 2. So 0 to 2. Now, where does x go from? Well, we're going to go from x equals y, which is really the same as y equals x, over to 2. So we're going to go y to 2. Because remember, these are x equals. What about z? Well, it's still the same z. See, the inner layer is still going in the same up-down. So we're still going from this bottom surface to the same top surface. So we're still 0 up to 2 minus 1/2 x squared. All right, good. Now we're ready for our next one. Okay, so what's our next one? So we have dy. So we're going to look down the y-axis. We say, okay, down the y-axis, where does x go from? Well, in other words, lower value to higher value. We're going from 0 up to 2. Now, once we have a particular value for x, we say, okay, where does z go from? I'm going to go from the bottom, z equals 0, up to this top, which is z equals 2 minus 1/2 x squared. Now, go to the three-dimensional picture. We're going to move in the y direction. Now, y is this way. So I'm going to be moving, in essence, here, left to right. So I'm going to move from one side and go to the other. So the question is, where do I hit? What are the surfaces? Well, we need to have this surface here, which is y equals 0. That's where we start. And we're going to move across to hit this other surface, which is y equals x. Remember, we need y bound, so it has to be y equals something. So y equals 0 up to y equals x. Okay, well, good. That one's done. Now let's go to our next one. So again, looking down the y-axis, so this is what we see. We say, all right, now, where does z go between? Where to where? Well, it's going to go from 0 to 2. All right, well, that's great, 0 to 2. Once you have a particular value for z, where does your x go from? Well, we're going to go from x equals 0 over to this curve. So that's x equals 0 to square root 4 minus 2z. All right? So that's 0 to the square root of 4 minus 2z. Now, what about y? Well, the answer was we're still moving in the y direction between the two curves. 0, sorry, I said between two curves, between two surfaces, which is y equals 0 and y equals x. All right, great. Well, we're making good progress. 2 to go. All right, what's the next one? Well, we're going to look down the x-axis. So down the x-axis, that's what we see. Great. And now we say, well, where does y go between low value to high value? 0 to 2. Okay, now suppose you have a y value. Where does x go between? Where, well, where does z go between? Because we're now on the z. Well, we're going to start at z equals 0. Good. And go up to this curve, which is z equals 2 minus 1/2 y squared. Okay, now back to our 3D picture. And we ask ourselves the question, where are we going? From where to where? Well, we're moving along the x direction. So here's our x-axis. So we're moving front back. So as we move front back, we're going to hit the two surfaces. There's this back surface, which is coming from x equals y, and this front surface, which is our curved surface. So we need to solve for those in terms of x. So we're going to start at x equals y, and then we're going to move to the front surface, which is the square root 4 minus 2z. Okay, good. One more to go. One last one, and we'll be done. It's kind of sad to think we're going to finish. Well, don't worry. There's still more problems to do after this one. So, what's the last thing? Okay, so down the x-axis, this is what we see. Say, all right, where does z go from? Low value of z to the high value of z. 0 up to 2. Okay, once you know your z, where does your y go from? All right, well, we're going to go from y equals 0, which is over here on the left-hand side, to this surface here, which is the square root of 4 minus 2z. All right, and now we say back x. Where does x go from? It's still the same surfaces, and so we're going from x equals y to x equals the square root of 4 minus 2z. And we've done all possible ways to write this as an iterated integral. And at this point, we're like, wow. You'll notice they're all different in terms of the bounds, which goes to show you it's not easy to switch bounds. It's not just a matter of like, oh, I'll just, move things around. No. You have to pay attention to your shape. Another thing you might notice is that some of these things are simpler than others. So for instance, this last layer here, last iteration, there's lots of things like the square root of 4 minus 2z, the square root of 4 minus 2z, and there's a y there. On the other hand, look how clean this one is. There's no square roots involved, and all these lower bounds are zeros. We definitely approve, because 0 is a wonderful thing to work with. So yeah, choosing an order of integration can make a big difference in your setup and how it looks. And so be careful, right? Be the right amount of careful. Whew, wow, what a problem. What a problem. That was a good problem. All right. Time for one more problem. One last problem to finish it up. Rewrite the following as a single integral. So we have integral 0 to 1, integral 0 to 1, integral 0 to 1 minus y squared, f of x, y, z, dz, dy, dx. And then there's another integral, 0 to 1, negative 1 to 0, integral 0 to y plus 1, f of x, y, z, dx, dy, dz. Okay, so somehow we've got to combine these two to one integral. Well, before we can combine them, let's understand what they're saying. So here we'll start reading off our bounds, and from the outside, okay, that says x goes from 0 to 1, and y goes from 0 to 1, and then z goes from 0 up to 1 minus y squared. Okay, well that's not so hard to see, right? Because what is this saying? Well, it says, look, in terms of the xy, we're going over a nice little rectangle, and we're going to go up to this curve, which is z equals 1 minus y squared. So if you think about that, it's an upside down parabola, but then you just translate it around. So there's our shape. When I say translate, you can just copy it back and forth because there is no x. So, beautiful. That's a nice, beautiful looking curve here. Okay. And I say curve, I really should be saying surface. All right. So that's that integral. What about the other integral? Well, we have 0 less than or equal to z less than or equal to 1. And then here we have negative 1 less than or equal to y less than or equal to 0. And then we have that 0 is less than or equal to x less than or equal to y plus 1. And here, okay, it's not so hard to figure out that one either, right? So we have x, y, z. And we can see, okay, just from the first two, z goes from 0 to 1, y goes from negative 1 to 0. So that says, oh, you start with a nice square here in the yz plane. And then we're told, all right, we're going from x equals 0, which is this part right here, to x equals y plus 1. Well, what does that look like? Well, if I look at the curve, x equals y plus 1, if we think about it in terms of the xy plane, what would it be? Naturally says that y equals x minus 1. So it would have a y-intercept at negative 1. And here, we would say when y equals 0, it would come and hit there at 1. Okay, so what we're seeing is sort of a little shape like that. All right? So this face here, this is our the face that corresponds to y equals 0, and the top place is, of course, z equals 1. This bottom is z equals 0. This back face is the x equals 0, and this slanted face, this is the face x equals y plus 1. We probably should have labeled things as well for this other picture just for reference. And so, all right, so we see here this part right there, x equals 1. This back part, x equals 0. This bottom part, z equals 0. Over here, we see, okay, that would be y equals 0. And then this slanted part, this curved part, is z equals 1 minus y squared. Okay, well, we say, hey, this is good, because notice they both have this part right here in common. In fact, they glue together at that spot. So let's mark this. We'll draw a picture which has both of them. So we're going to mark, they have this sort of common piece here. And then on one part to the, well, what we would call our right-hand side, it comes down. And then in the other part, it has a sort of diagonal aspect to it. Okay, so there we go. There's our region. It's just those two pieces put together. Now, it says do it as one integral. So there has to be a choice made. And the question is, which order to integrate? Now, there might be more than one correct order, but there are some orders which aren't going to work. So what needs to be true? We need to have consistent surfaces we go between. So, for instance, if the inside integral was with respect to z, we'd run into problems because at some points the top surface is this curved surface, but over here the top surface is this flat surface. It's an inconsistency. So if we integrated where the inside was z, we'd have to split into two parts. So we can't have z be the inside. All right, well, what if we integrated where the inside was x? Okay, could that work? Well, if the inside was x, we would see that over here, the front surface was very nice flat, corresponding to x equals 1. But on the other hand, if we move over there, we say, oh, the surface has now changed. It's now this other one at like a 45-degree angle. So when we integrate with respect to x, all right, this is with respect to x, we're moving the x direction. And here, this is with respect to z, we move in the z direction. We get inconsistencies. We see different surfaces. So it can't be that the inside integral is with respect to x, which means by process of elimination, we should make the inside integral be with respect to y. And you can check that if we make the inside integral with respect to y, we'll always have this piece here be our surface that's on the, say, the left-hand side, and this other piece here will always be the surface that's on the right-hand side. Consistent left and right, which means one integral to do. Okay, so we say perfect. So we're going to have an integral, 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 f of x, y, z, and we're integrating with this dy, and it doesn't really matter the next two, dy, dx, dz. Okay, great, good. And just for reference here, this is our y direction. So let's set up our x and z bounds. When we look down the y-axis, what do we see? Well, we're going to see this common piece that was on both. So down the y-axis we go, and we see, lo and behold, where does this go from? Well, it is this nice 0 to 1, 0 to 1 squared. Okay, so 0, 1, 0, 1. And now, how about where does y go from? Well, the low one, the left one, comes from this curve, or rather, excuse me, this surface. The surface where we had x equals y plus 1, which is the same as y equals x minus 1. So that's the lower bound here. The upper bound is this curved surface. Well, what is that? So that comes from this z equals 1 minus y squared. All right, so we just do some notes here. If z equals 1 minus y squared, that says y squared is 1 minus z. So y is the square root of 1 minus z. We can see here we're in the positive part. So we're going to have from y equals x minus 1 to y equals the square root of 1 minus z. And we're done. Wow. Cool. Cool. I don't know why I wrote the y equals. Okay. It's not bad to put it there, but I'll take it out. And what a fun problem. This one is fun because it's like, okay, you have a couple pieces. What do they look like? How do they fit together? And once you understand, life is good. And of course life is good. We're doing math. We're thinking geometry. It does take time to get used to this. And I think this is one of the parts about multivariable calculus that's one of the more challenging things, because you have to learn to think geometrically. And sometimes people aren't used to that. So don't rush, work through the process, try to figure out how do things fit together, what's going on, what do these surfaces look like. And with practice, it does get better. It gets fun. You can start to see how things come together. So keep at it. I am so glad you came, and hope to see you again. Bye.